Hi everyone, in this video I will present a short introduction for the layout exercise. For the layout exercise you will need this layout tool called KLayout. You will find the link to this website where you can download the tool on the PowerPoint slides, and when you open this website you will probably all be using Windows, so you find this Windows installation files down here. After installing KLayout, the next step is to open KLayout Editor. It's very important that we open KLayout Editor and not default or viewer, as the KLayout default is just the viewer and we want to do some editing, so we choose KLayout Editor. After opening KLayout Editor you get this blank view. We will now create a new layout by clicking File and then New Layout. As described in the exercise slides, leave everything to default. Now we see this empty layout. On the left you see cells. We will only be working with one cell, and this cell is by default named top cell. For the LVS later on, it is very important to rename the cell name to the name of the subcircuit. So basically, if your subcircuit is called inverter, you should rename this to inverter. You will see that this changes the name in the square brackets up here. On the right side, the layer list is empty right now. We will change this by clicking on File and Load Layer Properties. Then we will navigate to the exercise files and we will see only one file, which is the layers definition file. After opening this, you will see on the right side the different drawing layers. Next, we should adjust the grid size and the snapping. So to do this, we go to File and then to Setup. Here we go to Application and Grid and change the grid size to 11 nanometers, which is basically what you already see right now. So we click Apply and we click OK. And now we can zoom in, and we will have a grid spacing of 11 nanometers. We do this because the smallest size is 1 lambda, as you probably have already heard in the lecture or seen in the DRC rules. So 1 lambda in this case is 11 nanometers. So that's why we chose 11 nanometers. It just makes drawing in KLayout a lot easier. Now we will also make sure that our ruler snaps to this grid. When we use the ruler to measure distances or lengths, we will go to Edit and Ruler and Annotation Setup. And here we have to make sure that Snap to Grid is set. Now we can draw our first shape. To draw a shape, for example a box, we will first choose a layer, for example metal 1, and then the box. Now it will snap to the grid, and when we have like one grid spacing, we have 11 nanometers in width. And this is now 11 nanometers times 11 nanometers square. So if we want to draw larger squares, of course, we can also do this. To measure the length and the width, we can use the ruler and just measure like this, left clicking. So if we want to change or edit one of these shapes, we can use partial and then select one of the edges. And then we can just, like, for example, make the shape longer, or we can make the shape wider. Okay, now we have to save the layout. So we go to File, Save As. I will save this in the exercise files, and I will call this inverter, 22 nanometers. Save. Now we get this little dialog. We don't have to change anything here. Our format is GES2, which is like the standard in IC design. If you ever work at our institute, for example, or somewhere else and have to submit your layout to a fab for fabrication, they will most certainly ask you for GDS2 files. So yeah, that's the industry standard. For the DRC and LVS example, I will just be creating a 1 transistor cell. So for this purpose, I will be using this NMOS device. You can find this NMOS device by searching up here for NMOS, then just dragging it into the schematic. Double clicking on it leads you to the settings of this device. We should call it NMOS and add a width of 44 nanometers, for example, and a length of 22 nanometers. This is important for each device. Next, we have to create a subcircuit out of this 1 transistor cell. So we choose port, and then we add a port here, we add a port here, and we add a port here. So now we should also give each net a name. So we choose name, and then for this example, this will be called gate. This will be called drain, and this will be called source. Next, we save this subcircuit NMOS. In the next step, we open a new schematic, which will be our top level schematic, and we search for subcircuit. We will drag this into here and then double click and select the just created subcircuit. We find the NMOS, open, OK. Now we have the NMOS. We don't have to do anything further. We just have to go to simulation and save netlist. Save netlist. And then open this netlist. When we open the netlist and take a look at it, we see a subcircuit definition here, and we see some parts around it which we do not need, so we just delete these parts and save. This netlist will be used for the LVS. So continuing with the NMOS example, I have already drawn a layout for the NMOS. What you see here are lines on metal 1. You see some contacts, and you see a poly gate, and for example a P+ layer for the substrate tap, so basically the connection to the bulk, and you see N+ for the source and drain of the NMOS transistor. Next we can, or we should, in between when drawing, we should always do some DRC checks. To do DRC LVS checks and also have a nice 3D view, we go to macros and macro development, and then we go up here to Ruby and right click. Right clicking, we then choose add location and choose the exercise files. Now we see 3 scripts which are for the 3 things we want to do, the 3D viewing or 2.5D viewing, the DRC and the LVS. So let's first do a DRC check. We open the script, we don't have to adjust anything here, we just press run from the current tab, and then we see this DRC result. We actually see that not everything is green. We have some numbers here. We have some DRC violations. We open this and then we click on the DRC violation. We can also now zoom in, and we see that when we click on this, that it actually shows us where the violation is happening, between which edges. So we see metal 1 spacing is smaller than 4 lambda, which is our error. We can check this now. We can use the ruler and measure the distance, and we see, oh yeah, it's only 2 lambda. And when we do this, oh, we see it's only 3 lambda. So yeah, we actually have to move this part to make it comply with the DRC rules. To do this, let's first delete the measurements, and then we can select this part and click on move, and then move the whole part. Maybe now we have to move it at least 2 to this side. So 2 to this side and 1 up. And then of course we should again adjust polysilicon layer beneath. Yeah, to get rid of this, just close the DRC window, and then so now we can go back to the DRC script, run the DRC script again. We actually now see that everything is green, we see no numbers, so the DRC passed. Now to view the 3D, we choose this 2.5D script and don't have to adjust anything, just press play, and we actually now see this. But you can also scale them using a slider up here, so basically, yeah, we scale it a little down so it looks nicer, and then we can see like a 3D layout of what we have drawn right now. Now we will take a look at the LVS. Basically, the subcircuit netlist which I generated earlier is called nmosfet.cir for circuit. We see the subcircuit netlist, and we see that it's called NMOS, and it has 3 pins: gate, drain and source. And we have these 2 lengths, so basically the width of the device and the length of the device. This is going to be checked in the LVS. We have to incorporate this information into our layout. The name of the subcircuit has to be the name of the cell. So we see this on the left here. So it's called NMOS already. If you want to rename it, right click and press rename cell, rename it. You also see this up here in the square brackets. Next, we have to set the 3 pins in our layout. For this purpose, we have the metal 1 or metal 2 label layers. To generate the pins, we just have to place text approximately where the pins are going to be. We choose text up here, and we choose metal 1 label as the layer. And then, for example, we generate the source pin, call it source, and then place it where source is approximately going to be. Next, we have to do this for the gate too. So we place this here for gate and for the drain. Having done this, we should be ready for our LVS. We can, of course, again check if we actually have the right length and width. So ruler, this is our polysilicon overactive. So this part is basically our gate. We can check our gate length, which is 22 nanometers. This is all right. Our gate or transistor width, which is 44 nanometers. And this matches exactly what we have in our netlist. So everything should work out fine. Moving on to the script, we open the LVS script. We actually have to adjust something here. So down here we have the schematic and the schematic name, which is in this case inverter 22 nanometer QX per default. We are not going to use this subcircuit, but the subcircuit I generated earlier. And you can see up here it's called NMOSFET with an underscore. So we have to insert this name. You can save this also. I think you can just save it by right click and save. So then we run the LVS script and hope for the best. We see that everything is green and we don't have any numbers, so this actually worked well. Let's take a look what happens if width and length of our device doesn't match the original subcircuit netlist. So what I've done here now is I increased this by 1 lambda, as you can see. So basically, yeah, these are the old measurements, and now we see that this is 1 lambda more. So our transistor width is now 55 nanometers. When we open LVS now and run this LVS check, we actually get some error messages, so it didn't work. So when we look here, we see net drain is not matching, net gate is not matching, net source is not matching. And if we want some further information, through this line in the script, the netlist, which is extracted from the layout and which is then compared to our reference netlist, which we provide. The netlist is called extracted. And if we go into our files, our exercise files, and then open this extracted netlist, it says extracted by KLayout, we see that the NMOS device has a length of 22 nanometers, but a width of 55 nanometers.